Please make sure you have your copy of the molecular model tutorial. We're going to look at how polarity works. In particular, I want to show you how the molecular model kits work that we've been putting together so that you know what those models represent and how we can use them to look at a property of molecules called polarity and also intermolecular forces of attraction. Okay, so the first thing that we're going to look at, if you look on the back page, there's a table of electronegativities. You'll recall that what electronegativity shows you is how strongly do elements attract electrons in a bond. In the model kit that we're working with, these are the elements that we're focusing on. Hydrogen, carbon, nitrogen, oxygen, and chlorine. They're color-coded pieces. In other models that we'll work on, we'll also include phosphorus and perhaps sulfur. Now, the elements differ in how strongly they attract electrons, and that has an effect on the way that they make covalent bonds. So, when you look at the molecules that we'll be working with, these are the most common covalent bonds between elements like carbon and oxygen, or hydrogen, chlorine, oxygen and hydrogen, nitrogen and hydrogen. We find these bonds very frequently in the structure of many molecules. What the line between the elements represents is where each element is sharing one electron by overlapping their valence electron orbitals, a covalent bond. In our molecule kits, we're using straws to represent those bonds, where one element is sharing electrons with another. So for example, carbon, the black ones in our kit, and oxygen, the blue ones in our kit, share electrons by overlapping their electron orbital, and we're representing that by putting the ends inside the straw. That's the shared pair of electrons. That makes the covalent bond. If you want to see how to make these model pieces, you can look at one of my other exciting instructional videos. So let's look at these elements in particular. So I'm going to write the electronegativities of each of the elements by looking at the table of electronegativities. Carbon, for example, has an electronegativity of 2.50, and oxygen is 3.50. I'll write them in for all of the elements. Carbon 2.50, here's another carbon, and oxygen here is 3.50. Nitrogen is 3.07. Hydrogen is 2.20. Chlorine is 2.83. 2.20, 2.20. So what these numbers represent is how strongly each of those elements attracts the electrons that are in that shared pair, that overlapping valence electron orbitals, the covalent bond. Now, since one of them attracts the electrons a little bit more than the other one, that means that the electrons are pulled more towards one side of the bond than the other. The electrons are shared, but they're not shared evenly. One of them is sharing a little bit more than the other. That causes a change in the balance of the charges in that bond. On the side where the electrons are found being pulled towards, that side of the bond has a little bit more of a negative charge, because that's the charge of electrons. And when they're more on this side, we find more of a positive charge, more of a negative charge on that side of the bond. Over on the other side, when we pull the electrons away, that exposes more of the positive charges of the carbon. Positive and negative are not absolute opposites. They're terms of comparison, like tall and short. Sometimes carbon will be a little more positive, but sometimes, like in this example here, where carbon has the higher electronegativity, it's more negative compared to hydrogen. So it's like tall and short. Depending on who you're standing next to, you might be tall, you might be short. They're just terms of comparison, so we can see on which side of the bond are the electrons being pulled more. Between carbon and chlorine, there's a difference in the charges, and they're distributed more on the side of oxygen compared to hydrogen. And between nitrogen and hydrogen, nitrogen also gets that slightly negative compared to hydrogen. So the charges, when they're not distributed evenly, we say that there's polarity. Polarity means that the sides are different in charge. Polarity you might find in arguments too. You might have a polarized debate between pro and con, or yes and no. Anytime you've got polars, you've got opposites. And polarity, opposite charges across a covalent bond, makes these polar covalent bonds. Polar covalent bonds are one of the things that we look for in the structure of molecules to evaluate their polarity. The next thing that we look for is the way that the atoms join together and what effect that has on the shape and overall structure of the molecule. So what I'm going to do is I'm going to look at the elements that are part of our modeling kit, starting with carbon. Carbon is the black pieces that we're using in our model kit, and each of these prongs represents an electron that is one of the outermost electrons, one of the valence electrons. There are 4. The way that they're distributed in a tetrahedron, so that all 4 sides are even, no matter which way I turn this thing, it always looks the same. Carbon has 4 electrons that it can use to make chemical bonds with other elements. It can bond in all 4 directions, making carbon a very versatile element for building all kinds of shapes of molecules. Oxygen is a little bit different, though. Oxygen has only 2 electrons that are available for bonding. The other electrons are paired, and they don't form chemical bonds with other elements. We can't share the paired electrons, but we can share the unpaired electrons. So oxygen has 2 electrons that it can use for sharing. So when we see oxygen in a model, even though it has 4 ends sticking out, only 2 of them are going to be bonded to anything. The other 2, their negative charges stick out of wherever that oxygen is found in the molecule, and that affects the balance of charges in the overall shape of the molecule. So we have 2 electrons that can bond, and then these 2 pairs of electrons which don't, which give oxygen a strong negative charge somewhere in the molecule. Okay, another one, chlorine. Chlorine can make 1 chemical bond. It shares 1 electron with other elements. These electrons up here already paired, not shared. Big negative charge wherever you find chlorine in a molecule. Chlorine, since it only makes 1 bond, wherever it's found, it ends that part of the molecule. Hydrogen is like that too. Hydrogen can only make 1 bond. It has only 1 electron to share. The other side, no extra electrons to cause any negative charges to stick out of the molecule. Wherever hydrogen is, it ends that part of the molecule. And last, nitrogen. Nitrogen has 3 unpaired electrons that it can share. Its pair of electrons up here gives nitrogen a negative charge wherever it's found in the molecule. That gives a negative charge to that part of the molecule. So the first thing that we look at is polar covalent bonds. On which side of the bond are the charges found? The next thing that we look at is how does an atom arrange the bonds in 3 dimensions? What does it do to the shape of the overall molecule? The last thing that we look at is called symmetry. Symmetry, you will remember from your geometry class, has to do with how you divide up things down their middle in such a way that they have mirror image sides. So if I divide a person down the middle, their 2 sides, left and right, look like mirror images. When we look at molecules, we look for their charges. If we see that the charges are distributed evenly on both sides, left and right or top and bottom, then we say that that is an axis of symmetry within the model, within the molecule. Humans have an axis of non-symmetry. Our heads and our tails are different, and in molecules sometimes you have that as well with respect to charge. When you have one side that's more negative and one side that's more positive or flipped around, then you have an axis of non-symmetry we call a dipole. Di for 2, 2 poles, opposite sides. Something that has a dipole is more polar. Something that has no dipole, that is symmetrical, is less polar or nonpolar. Let's look at an example of a molecule that's very, very easy to make with the modeling kit. This is methane. Methane has 1 carbon and 4 hydrogens and these 4 bonds. I made one just by joining together one of my black pieces, the carbon, and 4 hydrogens with the 4 straws. It's very symmetrical. No matter which way I turn this thing, it always looks the same from the top. Methane is the gas that comes out of the gas jets. It's also the gas that's used to heat your home. So the first thing we're going to look at in our molecule is what are the elements and where are the charges. Each of these hydrogens has an electronegativity of 2.20. Carbon is 2.50. So between these 2 elements, the electrons are being pulled towards the carbon end of the bond. I'm going to draw that for all of these because they're all the same bond, hydrogen and carbon. So since the hydrogen is the one that's lower in electronegativity and losing the electrons a little bit on that side of the bond, each of these hydrogens is going to have a slight positive charge. On the other side, the carbon since the electrons are moving towards its side of the bond, there's more of a negative charge found on that side of the bond. Then what we want to look at is the symmetry of the molecule. How are the charges arranged in 3 dimensions? If I divide the molecule down the middle this way, the 2 sides are mirror images. There are 2 positive charges over here, 2 positive charges over here. I know it kind of looks like a guy doing jumping jacks. The way it's really supposed to look in your mind is like this. See the molecule? It's hard to show something flat and 3-dimensional at the same time. So this is really a 3-dimensional molecule, but it's kind of turned on its side, so it looks like the guy's doing jumping jacks there. Let's see if I can hold it the same way. Right, so that's how it looks. At any rate, when you divide it down the middle, these 2 sides look like mirror images. So we say that there's symmetry from left to right. There's left to right symmetry in this molecule. If I do the same thing this way and divide it top to bottom, again, the top and the bottom look the same with respect to charges. There's 2 positives, 2 negatives, so again, there's symmetry. This is a completely symmetrical molecule. No matter which way you turn it, it always looks the same. So this molecule is non-polar. There's no left, right, top, or bottom that looks different from the other sides with respect to charge. It's like a circle. A circle has 2 sides. It's got the inside and it's got the outside. The negative charge is on the inside, the positive charge is on the outside, so there's no left, right, top, or bottom with respect to charge in this molecule. The one right next to it in your diagram, cyclohexane, it's the same molecule but repeated 6 times. It's like 6 methanes all stuck together. And each one of them is very symmetrical and therefore nonpolar. If I drew those arrows like I did before, with the hydrogens being a little bit more positive and the carbons being a little bit more negative, the electrons are always being pulled towards the carbon side and away from the hydrogen side. That would be true all the way around the molecule. All of the carbons a little bit more negative, all of the hydrogens a little bit more positive. And when you look at the way that these charges are distributed, you'll see that, again, no matter which way you slice this thing down the middle, it's going to be completely symmetrical. You might wonder what's going on between the 2 carbons. Since they're both the same element, they have the same electronegativity. So the electrons are not more on one side or the other in that bond, at least not usually. So we are going to divide this molecule down the middle this way to look at its symmetry. Look, it's the same on both sides. So there's complete symmetry from left to right. And if I did that top to bottom, it would be the same thing. There's symmetry going this way. If I divided it this way or this way, any way I slice it down the middle, it's always the same. It's completely symmetrical. This is an example of a non-polar molecule because there's no one side, left, right, top, or bottom that's different with respect to charge. So let's find one that does have some polarity. Next examples: chloromethane and formaldehyde. So to make the chloromethane, I just took one of my methanes here and I took off the hydrogen and I can put on a chlorine. Now from the top, this thing looks the same no matter which way I turn it, but when I turn it on the side, now there's a clear difference. There's one side that's different from the other. So that might lead to some charge-sidedness, some polarity in this molecule. Let's take a look at the way that the charges are arranged. Chlorine has a higher electronegativity than carbon. This is 2.83 for chlorine, 2.50 for carbon, and hydrogens are 2.20. So if I draw the arrows, they'll go up towards chlorine, more negative on its side of the bond, more positive on this side of the bond. But you know, when you look at hydrogen in carbon, the hydrogen is a little more positively charged than the chlorine. That's a little more negative on that side of the bond. So, you know, is carbon positive or negative? It depends on who you're comparing to. The key is to look at the ends of the molecule. Here on this end, we've got these negative charges sticking out where those pairs of electrons aren't bonded to anything. Down here, all the hydrogens are positively charged. So if you divide the molecule down the middle from left to right, again, we see that symmetry that we've observed before. There's symmetry from left to right. But from top to bottom, now we've got something different going on. We've got a side that's much more negative and a side that's much more positive. That is a dipole. A molecule that has a dipole has some degree of polarity. And that charged sidedness gives this molecule properties that are different from the other molecules that don't have that property of polarity. Formaldehyde, that's another example of such a molecule. I have a formaldehyde molecule that I made here. Let me get this one out. This one has a new feature for us. It has a double bond. The carbon is sharing 2 electrons with the oxygen. The oxygen can only share 2 electrons. And when I draw that, or when I make that as a model, I take 2 of the prongs of the oxygen and attach it to 2 of the prongs of the carbon. Formaldehyde. This one is a molecule that used to be used for preserving biological specimens, but since it causes cancer, we don't use that for classrooms so much anymore. If I evaluate its polarity, I start by looking at the electronegativities of the elements. The oxygen is 3.50, carbon 2.50, hydrogen 2.20. The electrons are being pulled more towards the oxygen side of that bond, so there's more negative charge than positive charge down here on the carbon, but between the hydrogen and the hydrogens are more positive, carbon more negative, so the charges are distributed like so. Oh, and look up here, we've got these pairs of electrons not bonded to anything. Those negative charges sticking out of the molecule give it a sidedness. Down the middle, it's symmetrical, just like before. But from top to bottom, we've got that dipole. We've got one side that's more negatively charged and one side that's more positively charged. You can evaluate the polarity of a molecule by looking at the electronegativities, which side of the bond is positive and negative, how are those bonds arranged in the three-dimensional structure of the molecule, is there one side that's the same as the other, is there one side that's different from the other. All of those go into evaluating the polarity of a molecule. What you can try to do yourself is find the symmetry and polarity, or symmetry and dipole, in molecules like water and ammonia, or acetone, or butane. Try drawing those yourself and then come back and check and see how you did. Go ahead and turn off the tape now, try it yourself, and then check your answers. Okay, let's look at water and ammonia. Water is the classic example of a molecule that has polarity because the hydrogen with its lower electronegativity and its oxygen with its higher electronegativity, in fact it's the second highest on the periodic table, pulls electrons much more towards the oxygen side of the bond than the hydrogen side. So we've got positive charges on the hydrogens, negative charges on the oxygen, and then these negative charges sticking out of the top of the molecule. If we look for the sidedness, if you divide the molecule down the middle, mirror image sides, symmetry from left to right. But if you divide it down the middle this way, from top to bottom, very clear dipole. There's a negative side right here, positive side on the bottom, very strong dipole. Water is a polar molecule. When we did our experiment in class where we took the balloon and we ran a stream of water past the balloon attracted to the water because of this polarity property, this charged sidedness in water. It's like a little magnet, only not magnetic attraction, it's electrostatic attraction, but because of the polarity of this molecule, it was able to attract to the charges in the balloon. Ammonia, much the same story here. Nitrogen, just like oxygen, a very high electronegativity. It's the third highest on the periodic table. And these hydrogens with their lower electronegativity, all the electrons being pulled away towards the nitrogen. It's got that one pair of electrons up there that's not bonded to anything. Each of these bonds with the slight negative charge, each of these hydrogens, the positive charge side. If you divide it down the middle, it's completely symmetrical from left to right, as we've seen in all of our other cases so far. But top to bottom, there's a negative side and there's a positive side. So there's a dipole. These are too small and easy to look at molecules. Let's try one that's a little bit bigger and harder. Acetone, fingernail polish remover. So if I go around and look at the electronegativities of the elements, 3.50 for oxygen, 2.50 for carbon, 2.20 for hydrogen. Between the oxygen and the carbon, the electrons are pulled more towards the oxygen side. Between the carbons, they're the same, so we don't have to worry about them. The electrons are pulled more towards the carbon side because of its higher electronegativity, and away from the hydrogen because of its lower electronegativity. So now let's put on the charges. Negatives on the side for oxygen, positive on the side for carbon, positive here for hydrogens, and then negative for the carbons here. Some negatives in there. Okay, so now I'm looking to see symmetry and dipole. Pretty obvious symmetry down the middle here, like so. Oh wait, I missed something. What did I miss? Did you say, Whitey, you forgot to put those negative charges up there? That is true. Those unbonded pairs of electrons, very strong negative charge. Okay, now let's look at the symmetry. Left to right, symmetry. How about top to bottom? So if I divide it down the middle this way, very clear dipole going this way. There's a side that's got these negative charges up here, and then this side down here has got these positive charges, so there's a dipole. Left to right, it's symmetrical. So I could find the symmetry from left to right, and a dipole from top to bottom. How about butane? Butane, 4 carbons, each electronegativity 2.50. All these hydrogens, 2.20. So that means that in all of these bonds, the electrons are being pulled towards the carbon side. Hey, didn't we see this before when we were looking at methane? Yes, we did. This is like 4 methanes stuck together. So if I look at the charges on the carbons are all going to be negative, and the hydrogens are all going to be slightly positive. And we've got that same thing going on here where the charges are different, but they're distributed on the outside or on the inside. Like a circle has only 2 sides. This one doesn't have a top, bottom, left, or right. No matter which way I divide this one, there's symmetry going left to right. If I divided it this way right here, there would be symmetry going top to bottom. If I divided it going this way, there would be symmetry going this way. Every way I divide it down the middle, there's always some kind of symmetry all around. So this one is non-polar. Okay, so I went through that very, very quickly, I know. But since it's a tape, you can stop and rewind. You can listen to it again. You can come to class, ask me questions. I'm always around during homeroom. Come look for me so you can find out more. And we're going to use these concepts and evaluate the polarity of molecules in our upcoming experiments as we ask questions like, why do things mix, and how can you separate mixtures, and things of that nature. All topics relating to polarity and attraction between molecules. See you in class.